So now something absolutely different and totally unrelated. Machine learning guided equality iteration. We drew sticks and I lost, so I go second. What I want to present today is also related to scalability challenges of equality iteration. And here I start with the classic problem. We want to prove equality between two different terms. We have the start term and the goal term, and then we run the equality iteration, or at least we want to run it, but, well, the world catches fire and we run out of memory. And this challenge has been recognized by this guided equality iteration paper, which was just mentioned by Thomas Koehler and et al. And what I found in their research was that for relatively simple goals, like this is related to tiling a loop or matrix multiplication, that, well, even very simple operations take very, very long, consume a lot of RAM, and as you can see here, can generate a lot of data. And that also relates to that most of these are even unsolvable on like very relatively beefy machines in a reasonable amount of time. So what they came up in their work was having a guided equality iteration where we introduced these guides, as was previously mentioned, provided by human expert so that we don't have the huge problem to solve, but we try to go in tiny steps that are each feasible until we reach the end to have a better chance at solving the whole thing. So what are these guides? And I want to go a bit more in detail, and these intermediate goals or guides lie along the rewrite path of the whole problem. At least that's where they're supposed to lie. So they can be either some concrete term that say, hey, this term I want to prove now, then this one, or they can be kind of sketchy with holes. So this one here would be a concrete term with you have like a map, a loopy program, and everything is concrete. But then we can turn it into a sketch by introducing question marks where we say, I don't really care what's in there, but I want to do equality iteration until I have something that's kind of this shape in the EGRAPH, and then extract that and move on with the next step. And this also allows the author of the sketch to be much more imprecise in their sketch and give more leeway to the equality iteration itself. So this is expert-guided equality iteration, but you can see in the middle there's like a human, and let's get rid of the human because we have the problem, these sketches, writing those, it takes a lot of time. It's not very easy, and it's not very beginner-friendly, and you need domain knowledge about what problem you're trying to optimize, because maybe you have a Zelinsky compiler, as mentioned, that's more about like reshaping a geometrical problem or a loopy program, or we've heard about like biochemistry today, so or chemistry, all not things that are easy to pick up in an afternoon. So what we propose is machine learning guided equalization, where we take the human and replace it with a machine. So yeah, I've heard you have to have sparkles nowadays for this. So yeah, we replace the human with a machine learning model that generates, based on the start and goal term, these guides instead of the human. So let's think about what the model should do. Well, it should generate as a suitable sketch. Well, great. Ideally based on the start and end goal term. So what do we need from the model? Of course, generate guides. That's why you're here. It can deal with terms, and that's very interesting because terms are not inherently like flat text as you would expect from a large language model, but they have a tree structure. They also should be somewhat performant because we don't want to run like a cluster of a supercomputer for solving relatively simple problems. And hopefully it builds on pre-existing work because we don't want to reinvent everything. So when we go to the shopping list, with this shopping list to the zoo of ML, what can we pick? Well, we could go with classic ML, like there are decision trees, Bayesian learning, all these, well, classical things, and of course neural network and deep neural networks. And since deep neural networks are especially like proven to be able to generate complex structures, including images, graphs, and of course text, we went the route of neural networks. But then again, now you've gone down one branch, but there are many options to choose again. So we could go with an LLM, and that has the advantage, well, it's readily available, but it only processes everything as a linear sequence of text. Like we've seen, we put in S expressions, and we have lots of brackets in them. We also have the problem this discards completely the AST structure and needs to recover it by interpreting the S expression itself. Training one at home is also, at least for most people, prohibitively expensive. Even fine-tuning one can be very costly, computationally speaking. But lots of performance engineering has gone into making it fast, and we would like to have that. And it obviously can produce things. On the other hand, we have like graph neural networks when we go the other route and say, hey, we want something to take advantage of the structure. These work on general graphs. They can use the AST structure to some degree. They can be more economical when they're like smaller and more dedicated to the problem. But less work has gone into optimizing these things. And also the generational capacity is somewhat limited, I'd say. So what we've done is come up with something that lives in the middle, what we call a tree transformer, building on prior work, that works on trees, uses the AST structure, should be economically to run, but uses some performant components from existing transformer and LLM architectures, and also has a similar generational capacity. So we call it a tree transformer, and here's the pretty picture for it. I'm certain everyone understands it, and I have to explain nothing. So this general structure of this is a decoder with a transformer decoder with self-attention and 2 cross-attention layers. So I mentioned in the start that we want our model to generate guides based on a start and a goal. So these are for us 2 different inputs we want to give the model. So we have at the left and the right, but they both take the start and the goal term and feed those into the autoregressive decoder on the left side. And these 2 cross-attention layers pay attention to what's being given from the 2 encoders. So we generate each node of the AST of our guide node by node. And this also has the advantage that we never have to care about being syntactically correct, because we directly generate the tree. We generate the partial tree, we feed it back in, and autoregressively we can generate the whole tree. So here is how this works. We have at the start, then we add a node, then this creates 2 nodes, and so on. So in addition to this, we also use a tree-specific attention, because textbook attention, like something like rope attention, only encodes the linear distance between 2 different positions. But what we use is something called disentangled attention that gives us the option to encode additional positional encoding in the model. This allows us to include ancestor-child relationship of the tree in the model, but also sibling-to-sibling order between different nodes. So now that we have a model, we also need training data to feed this whole thing and even train it. So we want these triples of start, guide, and target, but there's no large pre-existing data set for most problems they want to tackle. We're dealing with languages that have very, very few users, so we need to generate the training data ourselves. And here we can use equality saturation to generate training data for later to use it for equality saturation, which I think is nice. So we seed an EGRAPH with an initial term from the language. And what we do then is we grow the EGRAPH by applying rewrite roots as in a standard equality situation. And at some point, we reach a limit of the size of our EGRAPHs, and we start extracting from one E-class term pairs, where we take an E-class and we pick 2 random terms. And we do this multiple times from that, we get the explanation between the equivalence between these two terms. And this sequence of rewrites we can slice up into nice triples, where we take the middle as the guide, and we have the left and the right as the start and the goal. And from that, we can generate training data quite easily. So I now come to the implementation and training. All of this is done on the RISE language, and we have about 8 million training tuples we're working with, which of course we can scale this up pretty easily. It's very easy to parallelize, because once we have the eGraph, we can throw it on many machines if we want to, and just sample more or do this process with different seed terms. The model is also relatively small, meaning for a large language model size, it's really small. And we can train it like in 2 days or even less on a consumer GPU, which is very nice to iterate and also to run it later in inference, which makes it small. So what we see is that the structure matches for the higher levels. So these are, for example, 2 ASTs that we have here. On the left side, we have the ground truth of the guide, and on the right side, we have the generated one. So we have, under higher things, we have like smaller mistakes still. And again, we are in a relatively small model yet. And yeah, here's something, we have an additional node that's generated here. But as we go down, we lose, so these two are completely different, because we have a let that's swapped with an app, and from there, the generation breaks down. But what we think and what we aim to do is like this shouldn't be that big of a problem, because we can reintroduce sketchiness because we have access to the output probabilities of the network. Meaning, if the network becomes uncertain about generating the next token, we can continue, but we can remember that and later replace this subtree of the tree with a sketch or a hole. So, yeah. So, for the next steps we want to go to, we have this working prototype model. We can generate these guides from start and end terms in the RISE language. We want to scale to larger jumps. At the moment, we only have a relatively small rewrite distance between the two jumps. We are looking for metrics for how good our generated guides are, which is important for our evaluation. Then we can actually start evaluating these guides beyond just pure similarity to the guide, because even if the model generates something else than the ground truth guide, it could still be a very useful guide, and we would be very happy with that. So, and you can find the code and parts of the data set. It gets updated quite often. Check it out, and thank you for listening.
Thanks for the great talk. I'll start us off with a question. I was very interested to see that for generating the training data, from a single proof trace, you generate a bunch of triples, sort of regardless of where the, I guess, the intermediate term appears in that rewrite sequence. Was this, like, obviously, you know, you want a lot of training data. This is the way to get the most. Do you have any, like, sense in terms of, like, how valuable a particular tuple is to have in the training set, right? Like, yeah.
No, we don't. And at the moment, we have not run into the issue that we have too much training data and we need to filter down. But that's certainly an option we might look into to prioritize those that are the most novel or that provide some insight. But at the moment, we try to use what we can and hope everything contains at least a little bit of insight and improvement. But that's certainly an option we can look into. Yes, thank you.
I have one more question for the... Oh, wait. Okay.
This is really cool. Fantastic talk. Maybe building on Max's first question. Sorry, Max, I'm being a bully. So when you extract the proof, Egg makes a effort to find like the shortest proof. Like if you had magically run the rules in just the right order, this is what you would have gotten. And I wonder to what degree that means the targets you're looking at are sort of trying to find like fast forwarding patterns or like rule fusions that allow you to skip a lot of intermediate steps. Does that make sense? Or?
Yeah, yeah.
And I was trying to figure out the way that relates to the way I understand sketches, like in the earlier, like Thomas's early work in Rise and Michel and everybody, you know, the whole group, being used often more like trying to find, you know, get to a normal form or something related to like the cost function where I happen to know this shape of program is going to be very efficient. And so I guess I don't quite understand if there's a connection between this kind of fast forwarding thing and the way sketches are often used for like hitting a normal, or like hitting some form or some invariance that happened, or you know cost will be low.
That's not a way we have thought about it, to be honest. But it would certainly make sense that like by trying to find the shortest and most efficient rewrite path, we will get something that is kind of in this, it lies in the space, that it's shorter and more direct. We kind of trade this off by how we slice up the training data, of course. If we take bigger jumps and take something in the middle, then of course there's more distance between that, and that's one dial we can tune. But at the moment we are only taking very short jumps, which equate to, of course, to more iterations that need to it may run. So no, but I think it's a good thing. Let's talk about that later.
Cool, great talk again. Yeah, sorry, Max.
It's okay. Now I'll ask my other question. One sort of difference between, at least what I understand of this approach, is you want to train your model on data that pertains to the domain that you're working on. Is that correct?
Yes, we have a domain-specific model for each language. Yes.
Yes. So is there an opportunity for sort of cross or pre-training, right? Like if I had one for a domain that was, you know, similar-ish, like for example, you know, a lot of domains have things about addition and multiplication and these commute and associate, right? So could I sort of take a pre-trained model and then augment it in my domain, but you know, it has like, you know, it's pre-trained on a sort of more generic domain?
So that's a decision we made not to do, because we want to keep the size of the model small. And if we make it more general, then we need to increase the size of the model, which means we both need more training data and more compute, and we try to avoid it. And we try to follow the mode that we have a specific model that's good at only one thing, and that's why we can keep it small. Especially because we don't want to run into the issue that, well, our equality saturation only takes 5 gigabytes of RAM, but we need 80 gigabytes or 320 gigabytes of language model to solve that, which kind of, well, I mean, that's, you can do that trade-off, but then I don't think it's fair to say, no, my equality saturation doesn't take a lot of memory because it hides it in the model.
Thank you for the great talk again. So kind of building off that, or I guess similar, is so the model is trained on a language, or each domain's language, but then I guess similarly, the models, like the training data is dependent on the rewrites available, because whatever rewrites you have, you're going to generate like different guides. So, and then I guess like if you added in a rewrite now what a good guide is, your model would. Basically, I guess, what is the interplay there of like, if I go and modify my rewrite set, how useful the model being able to predict the guides is?
So the model is definitely trained on the set of the language, the rewrites, and to some degree, most likely also on the scheduler. So this is baked in. Changing the language would just completely break the model. Yep. But adding one rewrite or another, well, you most likely won't make it that much worse, but the model isn't trained to take advantage of these, to generate clever sketches to take advantage of these rewrites. Then again, if you have a system where you regularly solve the same thing in the same language, in the same system of rewrites again and again, then I don't think that would be too much of an issue, but as it's now, you bake those rules into the model. Yes.
Yep. Thank you.
Okay, let's thank the speaker again.